All right. So sometimes people ask me what it is that I do for a living. Uh, and I always find it very challenging to actually answer that question. Um, Not because it's particularly complicated or shady or anything else like that. It's just that it's hard to explain to people who don't work with this stuff on a daily basis, right? Um, I use the analogy of a car, very similar to a mechanic who you drive your car into when it doesn't work. You understand how it operates, you understand, how the functions of the vehicle work, and you understand certain concepts about how cars work, but chances are pretty good that you aren't familiar with combustion engine internals. I barely am, and I'm inclined to be mechanical and stuff. And I come from a long line of mechanics, people who are engineers and draftsmen and machinists and all that other stuff. It's in my blood, right? Um, but also understanding that most people aren't interested or don't know, and that's okay. It's just that's what makes me a specialist. That's what gives me a good living, is that most people don't want to deal with the kind of stuff that I work on, right? But I'm going to try to explain it in a way that makes it a little more meaty than just saying, like, when I usually we just respond, oh, I work with computers. Sometimes I'll say I'm a data engineer. People understand the title, they don't necessarily understand what it means. um, but for the most part, it's very rare that I actually talk about what I'm doing, other than explaining that I take a bunch of data and do my best to make it graphs that are hockey sticks that go up because executives like that. All right, so here we go. In computing, you have three major components of any computer. You have the processor or processors, you have the memory, and you have the storage. Okay, so a computer does exactly that. It processes information and instructions, and where it does that is in memory, in what's called random access memory, RAM. That is a what's called a volatile area. It's the components in memory move that information very, very quickly, and it's basically the working table of what a processor is working on. But for stuff that it's done with, stuff that it doesn't have room for, whatever, it saves that off to storage. Storage is another device that is also measured in memory units, in megabytes and such, but the device allows for it to be, this information to be stored at state. So meaning that you can put it down, and even if the power goes off, it doesn't go away. You can turn it back on, right? The concept of a hard drive, or even a floppy drive, that any media that has that data at rest, that allows the machine to go off. Because whatever a computer is working on, as you know, if you turn the power off, or you unplug it or something, all that stuff that you were working on goes away, and the computer itself has to be rebooted. That information is coming off of that non-volatile storage. How do I start this machine up? How do I bring your operating system up, and like that, so that sort of thing. Now, in storage, a standard arrangement for storage, um, is a what's called a B tree, or a file tree. It essentially gives you a list that has, at the in the somewhere in, or documenting the metadata of what's on the drive. It will tell you what directories and what files exist inside the hard disk. It's telling the operating system where to reach this stuff physically on the disk, right? So it has a catalog of those names, and essentially says, okay, from position X to position Y, that is where this file with this name, these many bytes, all this other information, that's where that is stored. So that is how the operating system deals with what is on storage. And when you execute a program, what it'll do is you'll say, I want to load the file, or whatever is going on with the program. It looks at those files on the disk and reads them, and then takes action according to what the instructions are in the file. And those files are all formatted specifically for whatever program is being used, right? A lot of times it's open text and stuff like that can be read in a variety of programs. Usually if it's a document or something like that, that's something that many programs can open with and deal with and manipulate, and saves it. But programs that, or files that are proprietary, or are instructions specifically for a specific program, will not be useful to another program, right? So it launches up, it says, okay, you want to open the file 123.dll. If it's that's not a kind of file it can read. It opens it up. It's like, this is garbage. I have no idea how to work with this, right? Okay, that is file systems. That is storage. Okay, and storage is a big important thing in my world because lots of data needs to get stored in lots of places. And disk drives are, while they're cheap, they do have limitations. They go bad. You have certain speeds and response times, and of course, the more you store, the harder it is to keep organized, right? Now, the kind of data that I work with is what's called structured data. Not always structured, but what we're going to say as much. When you open Excel, okay, you have a spreadsheet, and there are columns, and each of those columns, it's a grid that you can define what kind of data goes into each column. You can have a header and a label at the top column. It's capable of doing that. So you can say this column is customer's first name, customer's last name, their address, all that other interesting information that you would put into columns. And the idea, of course, is that each column represents a select specific piece of data, usually what are called attributes, which are things about something, right? Your name, your age, your history, uh, what your certifications or education are, those sorts of things. And then a measure, something that you've done. Okay, so my name does not change. There only needs to be one record for me, but I do many things. I can make many orders from a website. So I would have one customer record with all of my attributes, but then every order I make, that is going to go into a different spreadsheet that says, okay, customer Brandon ordered 3 shoes on Wednesday the 7th and cost him $60. And then on Thursday, he ordered 3 shirts that cost him $40 and, whatever. Like, that is, those are the two most common use cases for data when you get right down to it. It's something about something, or something someone or something did, okay, or events that need to be addressed. In data theory, in database theory, you do what's called normalization. What the hell does that mean? Now you're getting into the weeds, man. Normalization is the idea that every entity is atomic, okay? Meaning that there are things about it that are unique, and that is all the information you want to keep in that record. If it's something else that is not unique about that, that is a different place to store it, okay? So again, we come back to customers, okay? I am a customer and I have all sorts of attributes, whatever facts about me that the company wishes to retain, my first name, my last name, my email address, or whatever. That is my entity. My previous address is actually a location, my many previous addresses. And the fact of the matter is, I've lived in many different places. So you're going to have a different table for that if you're normalizing the data. Now, I may only be interested in the current address. We'll just keep it in that customer table. But let's say I want to know every address that Brandon has lived at. Okay. So what you do there is you don't put the address in my information in my customer table. Instead, you create a locations table. And you have also what's called a customer location table to connect them to. So locations, of course, are unique, right? There's only 123 Main Street in Charlotte, USA. Okay. There can be many addresses, but the real question is, when did I live there, and where was it, and for how long, right? Every unique entity in one of these tables, a location and a customer, for this example, would get a unique value, would get a key value. There are many Brandon Sheetses, not many, but there are some. There are more than one, and there are many, say, New Londons in the world. Okay, so you don't want to have duplicates there. You want to make sure that those are unique ones, even if the names can be the same. That's how you make sure that there's uniqueness there. And you use those key values to join that information across multiple data sets. So in this particular circumstance, I have locations and I have customers, including me, and places that I've lived. I have lived at many places, and many people have lived at the places that I've lived at. So the idea with that third table is that you would have customer ID, whatever maps to Brandon, 123 Main Street, and maybe a time window, started living there, ended living there. And as long as those relationships exist, the customer that you're talking about with that ID value and the location that you're talking about, I can then join all that information together and know Brandon, if I'm filtering on just Brandon, Brandon lived at this address from this time to this date, and at this address from this time to this time, and from this address to this time and this time, right? You can put all that stuff together, but store the data in the most efficient manner possible because there are many situations in that case. It's called a many to many relationship where many people have lived at many addresses over the course of time, and many people can live at another address. Well, not only one person can live at an address, many people can live there, and I can have lived at many addresses. This is called rationalization, where we figure out what the data is and what it means. Because these are very simple examples. Things get very complicated in business. Talk about medical data. My God, medical data is absolutely crazy. Whatever all these different business rules that they have for it. But the core concepts are the same. And across pretty much every company, the core concepts are the same. Generally speaking, they're counting a number of things and they're keeping track of entities. They're keeping track of customers or clients or ambassadors or purchasers or whatever they want to call the person who's giving them money that they're interested in. Perhaps they're also keeping track of their own personnel. That'll be a different set of entities, employees and customers, even though they are both human beings, are different. You could get very aggressive about normalizing and say the person is an employee or a customer. It could potentially be both, right? Your system may not need to be that complex, though. That may not be data that you're interested in. But so on and so forth. They're counting dates, dollars, integers, basically like what the inventory is, what the model numbers are, whatever it happens to be that they're selling. Almost everyone that works with IT is working with a product that is for sale or some information about that product. And the underlying technology has not changed for over 50 years. The core paper that came out for the technology I work on came out in 1973 about what was called structured query language, and it was talking about these concepts. Now, when this stuff was developed, all of these concepts were very analog, right? That's why we still have images of the three and a quarter floppy disk, or three and a half floppy disk that you hit as a save icon. When I haven't seen a floppy in action for almost 20 years now. Same with CD-ROMs. Like I don't see those either. Um, we still refer to in data technology things like catalogs, indexes, lookups, all these concepts that would physically happen, because you can think of a database management system very much like a library. You, the user or the program or whatever, come up with a query, a question about the data that's in the database, right? And you have to know certain things about it. You have to know there's a customers table and an orders table and a locations table and all that other stuff. So you have to structure the query in a way that's going to actually parse, that makes sense. This data does exist somewhere in this library. But what you actually do, the way it actually works under the hood, is that you yourself are not fetching the data. What's happening is you take this query and you give it to the librarian, which in this case is the query analyzer, the governor, and it takes a look at that query and it parses it into assembly language, to its own internal language, and says, okay, I need to fetch this data. And it sends that information onto a worker process. It doesn't actually go back into the thing. But what it does is it comes up with a query plan. It says, okay, these are the results that are needed. What I want you to do is to go against this table and use this index, and this table and use this index, and this table and use this index. Perform these physical operations against the data and return the set to me. So in that way, the librarian, supposed, so to speak, is actually translating your needs to the database management system for it to go physically fetch that data off of the disk in the way that you asked for it, right? Now, I've mentioned indexes and catalogs and such. These are all library concepts. So indexes are probably the most important thing in that regard, and data types are probably another one, but we'll get into that in a second. Indexes are like this. I go to the library, and the library, let's say I'm in the fiction section, and I'm looking for a book called Green Eggs and Ham. The problem, of course, in the fiction section of a library is that it's organized by the last name of the author. So if I don't know anything else and there's no other resource for me to go to, and I'm looking for that book, I have to scour the entire fiction section of the library looking for a book called Green Eggs and Ham until I finally get to the S section under Dr. Seuss, who wrote that book. Finally, pulled that out. That's called a scan, a table scan in particular in data management. The idea there is that you know that the record exists, or it may not exist. You're asking you're asking the librarian for a book about about green eggs and ham, but there's nothing for the librarian to refer to in this case. So they have to tell the worker, go look through the entire library until you find one of these books. And if you find any of them, bring them back to me. Okay. But we know we don't do that. What do? Well, in a library, at least the old days before the computer kind of took over this function, you had what were called index cards. You had an index catalog, which was usually a cabinet of these, 3.5-inch cards, right? That you can still buy. And they'd be on a rail and they'd be organized. And in this case, what you would say is, okay, well, I know the title, I don't know the author. I go to the index that shows all the titles of all the books that are in the library and then tells you where to find them, who wrote it, that sort of thing. So rather than go scour the entire library, the librarian knows, well, you know what, I have an index on titles. I'm looking for the title. So I'll go to the index or instruct the worker, or whatever it is. They go to the index, they open that index card kind of catalog up, they look up green eggs and ham. Oh, that's under S over in the, quadrant 4 or whatever. And it'll also have other information in there. It'll say who the author was. It'll have the year it was published, maybe the publisher. So, of course, with that information that's on that card, now I can know exactly where to go. That's called a lookup seek, right? So I have looked this up, I've taken a look on the card, and now I go and seek against uh, the library because I know roughly where it's at. This says it's in section 7 on shelf 3 or whatever. I just go to section 7, shelf 3 instead of scouring the whole library. But here's a fun one. If all I need to know is who wrote Green Eggs and Ham and what year it was published, that index on the card covers that query. So I don't actually need to go find the book in the library at all to get the information that I'm asking for. I can go to the index and say, okay, Green Eggs and Ham, here it is, written by Dr. Seuss, and it's published whatever it is, 1962 or something, right? It's all the information I needed. Shut the index and leave. I don't need to go to find the book in the library to do anything else unless there's something that's in that book that is not in the index. And you could have multiple indexes. In theory, you could have an index on year published, and then you probably want it sorted by title or something. So if you're interested in books, all books that were published in 2009, you could potentially have an index on that. Or books where the first name of the author is Doctor or whatever. You could have an index on that and look up that way, right? There's all sorts of different ways that you can index. The problem, of course, is index maintenance. So in this analogy, the library, the shelf in the library, and the ordering system, what we would call the key or the cluster rather on that data, is how it's physically organized, and that has the entire record. That book, of course, is the entire record. It has all the stuff in there, right? I can find out everything I need to know about that book in the book, right? Makes sense, but stay with me. So anytime I'm using an index to find information, if that information is not contained in the index, I have to go to the source itself against what's called the clustered index. That is where all the data is actually stored. How that clustered index is organized really tends to change how the system performs in terms of retrieving that data. And of course, how much data is in there and what you're trying to join against and all those other things. So you spend some time thinking about structure of data in terms of how you can design this and how you can design it to be better. Most of the time, though, you're working with legacy systems, and that's the issue. That is the biggest issue. Some of this stuff has been around for 50 years. One of the oldest systems I worked at was worked on was at Nordstrom. It was in store one. They were decomming a mainframe. This was early 2007 or something, and they still had the spool systems. You know, the stuff you see in the old 80s and 90s movies. They still had these giant cabinets of tape drives, and it was all this giant basement of this huge department store that had been turned into one giant mainframe was getting reduced down to a box the size like this. IBM wasn't giving them a cut savings on any money. They saved a lot of power, of course, moving everything to regular storage, but it's a legacy system that was just micronized because the hardware has gotten so much better, right? And of course, it's gotten so much better since. But the amount of data that we're collecting has also grown rapidly as well. So it kind of seems to be that we're not really making much ground in terms of performance because the number of records and the width of the records we're collecting is so high. We collect everything now. No, nothing gets thrown out. Nothing. Everybody's like, I want to be able to go back to the beginning of time. Okay, but understand it costs performance to do so, and that is the trick. The other part, of course, is that all these things are built upon previous solutions over and over and over and over through many iterations throughout the years. And the types of ways that things were solved in different ways, different clever ways, a lot of critical thought, sometimes not, but mostly good critical thought. Solving a problem was not always the way to do it in a different system. And so you have all these different platforms, different standards, different ways of spitting files out. They've gotten better with standardization. They've stopped trying to reinvent the wheel. JSON is the new one, but XML was previous to that. And there's other stuff that they do with this data. It's just land on one. CSV, old comma separated file or tab delimited files, work great. Can we stay on those, please? You get some stuff from old systems like ragged write formats or fixed width formats and stuff like that. It's just old stuff that you just have to work with. And that's the big trick with this job, is that usually you have a bunch of old systems, all the stuff that's been built on top of itself, and they're all kind of solving their own problems and figuring out ways to make these things interface and talk to one another and come out with a new set of data, a new system, a new application, whatever it happens to be, an improvement against the current one. Um, it is not sexy work. It is definitely dealing with a lot of numbers and texts and a lot of grids on screens and code. Very little graphical stuff in my field, but I like it. It's puzzles. It's I want to know how to fetch this information. I want to do it quickly. This information needs to get loaded and saved. I need to do it quickly. It needs to get from here to there, and it needs to look a certain way. They need to tie. They need to match. They need to be reliable. And that is the nature of my work. So. Uh, that is about it, though. I could go on about the trials and travails of what's going on in my industry. I won't do that here, but just to help maybe make you understand a little bit, there is method to the madness. It is not rocket science, but it is important work that without it, companies freak out. They don't think about us very often. They don't think about engineering in general. We're a cost center. We cost money. We're like the mechanics in the fleet. It's just, yes, we have to be experts, and we expect a fair wage and want to have a good life and all that other stuff. But we make you millions of dollars, and it's not. I don't think it's unreasonable for us to ask for a comfortable living if we're making you all that money. But of course, they're grinding everybody down, as with everybody else. Uh, but it is complicated work, especially because there's so much legacy involved. Part of the struggle with AI is that AI is only capable of understanding what it already knows. It's working almost completely from memory. It does extrapolate based on that memory, but a lot of my job is intuiting what I think the customer meant, what the customer wants, and what the previous engineer meant, what they were trying to accomplish, and what the business concepts are, what the thought process was behind it. Why are things called this? What are things that could be called that a different way? Because these things don't always talk together. There's not always a firm relationship between these multiple systems, and sometimes you have to come up with one, and other times you're just trying to report in a way that kind of makes it look like it ties together, whatever the business requirements are. You're just working with whatever you have to come up with something new, but it's not something that can be programmed. There are inferences that can be made, and I'm sure the systems will get better. But for now, you're gonna need a human touch if you're dealing with serious data engineering, because the assumptions that AI makes are flawed very regularly, and you need an expert in place in order to make sure that even if you're leaning on AI to make things faster, that you're not screwing yourself by allowing it to make a decision that doesn't make sense. So anyway, that's it.